Hi, I'm Moresi. I'm here to talk to you about geoscience research, that is, reproducible, replicable, and reusable. So it's important that we understand what some of those terms mean. Let's start actually with reusable, because it is where we'd like to be. What do we mean by reusable research? Well, let's actually go back to Isaac Newton. Isaac Newton, famous in a letter to Robert Hooke of having said, "If I have seen further, it is by standing on the shoulders of giants." And of course, what he meant was when you do research work, you don't have to keep starting from the beginning. You have a whole heap of people on who you've trodden to get to the knowledge that you have right now. At least he meant something like that, didn't he? He's a bit of a strange character, Isaac Newton. He's also famous for having lectured to empty rooms. Who knew that that would be a thing? He did. Here's a different quote, and one that I think I like a little bit better, actually. It says, "The free sharing and teaching of open source is incompatible with the notion of the solitary genius." In other words, rather than standing on the shoulders of giants, we all contribute. Even lesser mortals among us actually have a role to play. We can contribute something, and people will build upon our work, right? But not if that work is not something that people know about or can use. So we have to make our work accessible in some way, and we have to make it possible for people to build upon it. So I wanted to talk about how that relates to numerical modeling, which is the area that I work in, and something that I've thought about a great deal. So the Underworld suite of software, which includes Underworld geodynamics code, groundwater code, surface process modeling code, and various ancillary bits and pieces that help along the way. We've designed that to try to make it as reusable as possible. And I want to tell you a little bit about what we do. Okay, so first of all, let's think about some of the terms, right? What do we mean by reproducible research? So what we mean really is that if I take an experiment, or in this case like a computation, and I repeat it, I do it again, I will get the same answer. Right? If I give you my model and you run it, you'll get the same answer that I got. And hopefully it's the right one. But the point is you can test that. You can be skeptical, you can run the code, you will get the same answer, and then you can think about whether you want to do that. As part of the AuScope SAM Cloud project, so we focus quite a lot on ways to make it easy for people to take codes other people have constructed and take models that they've built with those codes and be able to rerun them at different times and in different places, and to make sure that they get the same answer. As long as you can establish a sort of a pathway through the data so that people are able to initialize their models in the same way, 10 years later you should be able to run the same thing. That's really important. Okay, so they have to be the models themselves have to be written in a way that is accessible, but they also have to be encapsulated with sort of mechanisms for making them completely reproducible. So reproducibles, that's what that means, right? If you do the same thing twice, you get the same answer. Don't forget that if there is some randomness in the models that you set up, that doesn't mean that you'll get the same answer. It means that you ask your questions in such a way that they give you the same conclusion, regardless of sort of the numerical values of the output. All right, so that's quite an important distinction. Oh, well, what about replicating research? What does that mean? Well, these terms are, maybe they seem familiar, but there's this very specific meaning that's usually attributed to something like research replication. And it means something like this. If you run the experiment that I designed, but instead of using my code, you use your code or your methodology, then you'll get the same conclusions that I got. Okay, if you accept my premise about the experiment, you can reproduce it. Okay, that doesn't mean to say we have to agree on the meaning of that result. You may disagree heartily with how I interpret it, but we will run the same. If we run the same methodology, we run it, according to some agreed protocol, we'll get the same answer. We'll get the same answer. All right. That does mean something as well. We have to agree on what the uncertainties will be. What will we accept as the same answer? And this is a classic thing that we've done in numerical modeling with things like benchmarks, right? Where we establish a simple experiment that everyone can do. Everyone will get a slightly different answer, but we accept that there is a range of answers that is, that gives us an error measure, if you like, of the accuracy of our ability to model something. Okay. What does that really mean? Well, it means something else too, right? It means that not only do we have to agree on the way that we're going to sort of describe the model and describe the answers to the model. What is the acceptable range of outputs that we will accept as a passing grade, right? But it also demands that we describe the model in a way that we can implement with different underlying methodologies. So, for example, we just for the kinds of work that I'm very familiar with in planetary scale modeling, then one of the things that you really want to be able to do is to describe your model around the physics or the mathematics of the model and not the implementation. I'm not going to tell you how many grid points you need. I'm only going to tell you it needs to implement these equations. Okay, so that's the way to think about that is well-designed abstractions, well-designed ways of describing the model that are not especially related to how it gets implemented. So mathematical notation is one such abstraction, but I can tell you now that if I describe everything through equations, especially if they're all in weak forms or something, that's not especially popular. In fact, if I ask for a show of hands, everyone who would rather deal with mathematical equations than geological terms, everyone raise your hands. Yeah. See? We want something closer to the geological description than the mathematical one, but still we need to abstract our problem in that way. Right? Reuse starts to get a little bit more interesting. It means you can take my work and you can build upon it for your work. Right? So it actually has a lot in common with the idea of open source software, that there are no barriers that I impose on you that stop you from taking my models, my codes, and taking your ideas and using my work to build upon to your ideas. Okay, we are very familiar with that with mathematical. We go and get a textbook and use a mathematical model, right? But it's quite difficult to get somebody else's code and just start running it and do something useful for yourself. Okay, so one goal there would be to make significant research results immediately accessible to the rest of the community. All right, so if I publish a paper or somebody else publishes a paper one day, then it can be reproduced the next. We can use it in our work the following day. Okay, so we get a culture of sort of fast following, cooperative leadership, right? I do something and pass it on. And that really should shorten the path to research impact, which is something that we all want to do. We want to get the things that we have worked on out there into use by a whole different community as fast as we can. And it really does mean we're standing on the shoulders of giants, or actually, more appropriately, we are standing on a pyramid created for us by regular people, not just waiting for heroes to come along. It reminds me of something. It reminds me of the idea of fair data. Okay, so fair is findable, accessible, interoperable, and reusable, right? So if your data is reusable, so fair, it describes a pathway that culminates in reuse of data. And we have to think about how those requirements map to something that's not just a data set, right? It's something that has been measured and established, but is a model which contains a sort of a pathway that is full of knowledge and interpretation. It makes it a little bit harder to kind of stamp in this way. The thing about FAIR, though, we can learn about things from accepting the FAIR principles, is that it's not just available and persistent, right? It's richly described by metadata, metadata that's appropriate, that's possible to discover programmatically, but is meaningful both to the machine and to the human who wants to use that data. Okay, but there's always a but, right? So, well, I just have to sort of point out that there's a lot of ways people reuse models, and often the way that you reuse a model is a little bit different from the idea. I mean, there's interpretation involved, right? So, I look at these models. There's 3 different models here that come from the ideas of planetary dynamics, right? So the bottom is a flat Earth model. And it's really convenient to use. I mean, everything's easy. The equations are simpler. You don't worry about complicated coordinate systems. Very easy to set up. And actually, from a mathematical point of view, most of the results that you will get in a flat Earth approximation apply quite well in the spherical Earth. Okay, not exactly, and you have to do some things to worry about it. But there's very many cases where it makes sense to work in a flat Earth. Okay. So how would I use that flat Earth model to initialize or discover that model as being a starting point for one of my curvilinear models? Well, again, we need the right abstractions. And the reason that we can treat these as being equivalent is because mathematically we can write a set of equations which are independent of the implementation. You know, and the implementation here actually means the geometry of the model. Okay, so we can do that mathematically, and we can, if we write our codes correctly, and we've done this a little bit with Underworld, we can use exactly the same script, if you like, the same program to run either of those models, any of those three models. They differ by things like the mesh and how the boundary conditions are described, but they can all be written by the same. They can all be described by the same piece of code, and that's this little snapshot here that you don't need to read, but is actually identical for all three. Okay, so we change things like we describe things in terms of basic vectors, like a vertical vector for gravity and a boundary, an inner and outer boundary. That doesn't matter what geometry it is, right? So our abstractions have helped us to see an equivalence that would not be there if you simply, even if, you know, in many ways that you would look at this model, right? So you have to take that even for this simplest example, it can be quite complicated. So I want to summarize that. The reuse of models builds upon first being able to reproduce and replicate model results, and we've sort of looked at what that means. Replication itself implies that we understand what models, what the uncertainties are of the model, right? Because if there is either some randomness in the setup, or the system is chaotic and sensitive to the setup conditions, or we are genuinely replicating something where different methodologies are involved, then we don't expect to get an answer which is identical. We expect one that has identical meaning, and we have to establish what we how we view that, right? So the computational models, though, if you're going to reuse them, have to be both extensible, they have to be transparent, people have to understand what they're doing, and they have to be completely open. Otherwise you can't repurpose them for something else, right, if they're black boxes. So we don't want any black boxes anymore, that's the thing. And as I alluded to before, the findable part of FAIR, which we think of for data, is sort of relatively simple. It does imply lots of appropriate metadata, but it's not obvious for modeling that metadata is explicit, that you can really always rely on it. So if I tell you I've got models that are great for Mars, you might not realize that they could apply to the early Earth, right? Because I didn't tell you that, so the metadata doesn't contain it. So we have to be a little bit careful about how we do that. And in fact, we can think, there's a sort of philosophical reason for thinking that, right? That in most cases, or many cases, the meaning of a model is how it's used. Okay, so harping back to Wittgenstein's original quote, but that means that maybe the information that we try to codify into a model when we run it is not actually the most meaningful metadata that we can use to discover it and to apply it. And so in that case, we may want to we may not want to do this a priori. We may want to see how the models are used and build a collection of metadata based on how that gets used. In other words, we need to provide the models to people to browse, and then when they finish browsing them, we understand and retrospectively see what they were using them for, see what they identified in those models that we hadn't realized was there before.